Hello dear students, this time I again welcome you. It is the 7th lecture on vector calculus that we want to share with you. Previously we did the concepts of this del operator square, that was the Laplacian operator in previous lecture, and some application is there. Now actually we have to take the vector integration. Before vector integration, I thought in your syllabus, both in the 5-year integrated course students and this BTech students and some BSc students having this vector calculus as a course of study. There you have, it is mentioned that this solenoidal vector and irrotational vector. I have already defined this. What is a solenoidal vector? What is a irrotational vector? And you know that when the divergence of any vector vanishes, then we say the vector is a solenoid. And if the curl of any vector vanishes, it is 0, then we say it is a irrotational. And today I want to discuss with you some applications. You may come across some applications in your examination or in your books. You have also there in rotational and solenoidal these vectors. On the basis of this, I will discuss some applications. After that, we will come this vector integration. Okay, let us come and have some applications. Here I have the first application I want to discuss with you. It is the application number 1. It is if f1 and f2 are two functions of x, y and z. f1 is some function of x, y and z. f2 is also some function of x, y and z. Then you have to prove del operator dot del operator f1 cross del operator f2 is 0. In fact, you have to prove that divergence of this cross this is 0. What is actually this del f1? This del f1 is actually the gradient of f1. This is actually gradient of f2. In any way, let us have the solution of this. I will discuss the solution of this. This is the solution of this problem. We know del dot f cross g. Del dot f cross g. You have done this theorem in your previous lectures. In description we have written there the product of the divergence and curl of vectors. In product of the vectors, where we find out divergence of the product, curl of the product. In that lecture you will get what is del dot f cross g. It is actually equal to g dot curl of f minus f dot curl of g. Name this first. We will be using this fact. Now take this one. Now what is del dot del operator del f1 cross del f2? How you do it? On the basis of this, treat this as, you will treat this as your f, this as your g. Apply this formula, del dot f cross g. So del operator dot this cross this. What is this now? Your g is here. It is del f2 dot curl of f. What is our f? It is del operator f1 minus, then you have f. What is our f? It is del f1 dot curl of g. What is our g? It is curl of del f2. Okay, I am applying this formula with this, treating this my f, treating this as g, and applying this formula del dot f cross is g. Okay, now what is this? It is del operator f2 dot, what is this? It is curl of, when you have del f1, it is gradient of f1. It is dot del operator f1, it is minus here, del operator f1 dot curl of, it is actually gradient of f2. And before this, in previous lectures, you will come across a very important result that we did. We have solved it there. What is curl of gradient of phi? Curl of the gradient of phi, it is 0. This result we did. Curl of gradient of phi, this is curl of the gradient of f1. So what is this? It is your del f2 dot, it is 0 according to this, minus, it is your del f1, it is del f1 dot, what is curl of gradient of f2? It is also 0. So this is your 0 minus 0, it is 0. Therefore you have proved, hence we have proved that del dot del f1 cross del f2 is also 0. In fact, we have proved something this also. We can write we have proved this thing. This implies we have proved del dot, what is this? It is some gradient of f1. This is cross, this is gradient of f2. We have proved this is 0. But what is del dot this? We have actually proved now divergence of gradient of f1 cross gradient of f2 is also 0. That means this result we can state in this way also. We have proved divergence of gradient of f1 cross gradient of f2 is also 0. This is a very important result. This is we took it in application part. You will also remember for your MCQ purpose. This is also one application. Let me take now second application. Well, I will have now application number second. In application second, I will write here, if it is second application, if f and g are irrotational, then show that f cross g is what? Is a solenoidal vector. You are given that f and g are irrotational, then show that f cross g is solenoidal. How shall we deal this result? You see how we write solution. We are given that f and g are irrotational. When you have the irrotational vectors, that means curl of the vector vanish. If you have the solenoidal, that means divergence of the vector must vanish. Okay, you see how we go. Given that f and g are irrotational, this means curl of f is 0 and curl of the vector g is also 0. Why so? Because we are given that these vectors are irrotational. Now we have to prove that f cross g is a solenoidal. When it will be a solenoidal? When divergence of f cross g is 0. Now we find out, find out divergence of f cross g. That is, we write del dot f cross g. What is the divergence of f cross g? It is, it is g dot curl of f minus f dot curl of g. Previous result, what we used previously, del dot f cross g, it is g dot curl of f minus f dot curl of g. What is this now? It is g, curl of f is there 0, because it is f dot 0, that means it is 0. Therefore you have proved that divergence of f cross g vanishes. When divergence of any vector vanishes, what is the vector? It is a solenoidal. So what is here? What is your vector here? Your vector is f cross g. So this means that, this implies that f cross g is what? It is solenoidal vector. It is a solenoidal vector. So remember this also for your MCQ purpose, that if you are given that f and g are irrotational, then f cross g is always a solenoidal. Remember this. We have proved it in this way. Well, let me take one more example. I will name it third application. Third application I will write it is a vector field. A vector field is given by say it is f is equal to x square plus xy square unit vector I plus y square plus x square y unit vector j. Show that field is irrotational. That is, we have to prove that the motion of this field is what? Irrotational. So irrotational means we have to prove that curl of this vector vanishes. How will you go? You will write solution. Vector field f will be irrotational as usual by definition if it will be irrotational if curl of f is 0. That is, if del cross f is 0. Now what is our del cross f? We have curl of f, that is equal to del cross f. We write it cross product in determinant form. You have the determinant form of this. You write first row as usual, unit vector I, j, k, then components of this del operator, as you know, dou by dou x, dou by dou y, dou by dou z. You know what is our del? It is I dou by dou x plus j dou by dou y plus k unit vector dou by dou z. These are its components. Then f vector, its components. It is our f vector, right? It is xi component, x square plus xy square. Then it is j component, it is y square plus x square y. Then z component you don't have, it is 0. Now let us expand this by determinant rule. This is I unit vector. Delete this row and this column. It is dou by of 0 minus dou by dou z of what? Y square plus x square y. Then you write minus j. Yes, delete this row and this column. Dou by dou x of 0 minus dou by dou z of x square plus xy square plus unit vector k. It is dou by dou x of unit vector k, delete this and this, dou by dou x of y square plus x square y minus dou by dou y of x square plus xy square. Let us see what happens. You have this, delete this row and this column, dou by dou y of this, dou by dou z of this, then j times dou by dou x of this, j times dou by dou z of, then delete this and this row and this column. Let us see what happens now. This is I, this is your 0, you don't have z here, it is also 0. Then minus j, it is 0, you don't have z here, it is 0. It is k, differentiate this with respect to x, y square is 0, it is 2xy, minus differentiate with respect to y, x square is 0, it is minus 2xy. This is also 0. So you get curl of f vanishes, it is 0. So what does this mean? This means f is irrotational. So we have verified that this f is also rotational by applying this result, curl of the f is 0, and using the determinant formula. Okay, this was third application. I discussed it with you. Let us have now fourth one, application 4 I will take. Application 4. Application 4 I will take from some book. It is a fluid motion is given by, it is a fluid motion is given by V is equal to y sin z minus sin xi, y sin z minus sin xi plus x sin z plus 2yz unit vector j plus xy cos z plus y square k. You have to answer, is the motion rotational? Is this motion rotational? Let us see. To check whether the motion is rotational or not, we will go to solution. We will write the motion will be irrotational if curl of V is 0. That is, if del operator cross V is 0. Let us check. Now, what is del operator cross V? It is as usual determinant of unit vector I, j, k, components of this dou by dou x, dou by dou y, dou by dou z. It is what we did previously. Then components of V, I component, it is y sin z minus sin x, then x sin z plus 2yz, then this component xy cos z plus y square. It is I, delete this row and this column, it is dou by dou y xy cos z plus y square minus dou by dou z of x sin z plus 2yz, then minus j I will write, delete this column and this row, it is dou by dou x of xy cos z plus y square minus dou by dou z of y sin z minus sin x, y sin z minus sin x, then plus k, delete the first row and third column, it is dou by dou x of x sin z plus 2yz minus dou by dou y of y sin z minus sin x. Let us see it is simplification now. This is dou cross V we are finding out. I times derivative of this with respect to y, it is x cos z, x cos z plus 2y, then this with respect to z, it is also minus x cos z with respect to z minus 2y, y minus, I am differentiating this with respect to z, then taking this minus inside, then plus minus j, come here, derivative of this with respect to x, it is y cos z, derivative of y square with respect to x is 0, then z, it is minus y cos z, y cos z is 0, come here, then plus k, then derivative of this with respect to x is only sin z, Derivative of this quantity with respect to y is 1 sine z. So we have differentiated this applying the determinant rule. Okay, now this gets cancelled. It is I times 0 minus j times 0 plus k times 0. That means you get curl of the vector field V is 0, which means yes, V is irrotational. V is also rotational. This is how we check the irrotationality of a vector or solenoidal vector, where you have del dot this 0. Let us have some more example. Let me have this fifth one. It is if f is a x square y plus yz unit vector I, then plus xy square minus xz square j plus 2xy minus 2x square y square k is solenoidal vector. Find A. What is A? What is A? Also find curl of this solenoidal vector. Question is like this. You are given f is this vector. Given that it is solenoidal, for what value of A it is solenoidal? Is it? Then if it is a solenoidal, what is the value of A? And for that value of A, find the curl of this vector. Also find curl of the solenoidal vector. You see how we go. We write vector f will be solenoidal if divergence of del dot f is 0. When divergence vanishes, vector is a solenoidal. When curl vanishes, vector is a irrotational. If del dot f is 0, it is the divergence of f. What is this? It is I times dou by dou x plus j dou by dou y plus unit vector k dou by dou z. I am giving the value of this del operator dot what is our f? It is a x square y plus yz I plus xy square minus xz square j plus 2xy minus 2 x square y square k is 0. Now when we operate it, I dot I is 1, I dot j is 0. As you know how we operate the del operator, this will be this dot product. It is dou by dou x of what? A x square y plus yz, then plus dou by dou y of what? xy square minus xz square plus dou by dou z of twice xy minus 2 x square y square is equal to 0. Now differentiate this with respect to x. This does not involve x, so it is 0. Its derivative is 2axy. Now differentiate this y. It is free from y. It is a constant. It does not involve y. This involves y. It is plus 2xy. Okay. Now this with respect to z, it is free from z, so its derivative is 0. Here you don't have the z, so it is 0. We can take here 2a common. We can take 2xy common. 2xy is common. It is a plus. It is 2 with respect to x, 2axy. Yes, with respect to y, it is 2xy. You don't have z here. No, you don't have z. Yes. It is 2axy with respect to x, 2axy. It is 2 down 2xy with respect to y. Yes, we take 2xy common. It is then a plus 1 is 0. It is 2xy. Then 2xy is not 0. When you use it here, now your f at this value of a is this is f minus a is minus 1, a minus x square y plus yz I plus xy square minus xz square j plus 2 xy minus 2 x square y square k. Now you find out curl. Now we find out curl of f. It is now solenoidal vector. For this value of a, it becomes a solenoidal vector. So curl of this solenoidal vector will be now, it is what? Del cross f. You will do it because you did it in previous this example by taking the determinant rule. I, j, k components of this dou by dou x, dou by dou y, dou by dou z. Then components of f are this, this and this. Then take the product. You will find out it curl of the f. Well, let us have one more example. Suppose we have one more application. It is if a is a constant vector, if a is constant vector, a is constant vector and R is your xi plus yj plus zk, then prove that curl of a cross R is given, is 2a. Your a is given a constant vector. We go this way. We write, let us take, let a be equal to a1i, a2j, a3k be the vector where a1, a2, a3 are constants. We took a this. Suppose a is this. We have to prove that curl of a cross r. We'll first find out what is a cross r. A cross r, as per usual. A components of this first we write I, j, k. When we find the cross product by determinant rule, the first row is replaced by I, j, k, and a, the components of a, this is your a1, a2, a3. Then their components of r, which is x, y, z. Okay. Now compute this. What this will be? This is I times a2z minus a3y minus j times a1z minus a3x plus k times a1y. It is a1y minus a2x. This is your a cross r. Now we have to find out the curl of this vector. Now what is curl of? Now we find out what is now curl of a cross r. This will be determinant of usual I, j, k. Components of a, you took it a1, a2, a3. Okay. No, you have, sorry, I found it. It is this way. I will write here. It means actually del cross a cross r curl. This is I, j, k, component of del operator, dou by dou x, dou by dou y, dou by dou z. Then components of a cross r. This is your a2z minus a3y. Component of this is a3x, because this minus will go here, a3x minus a1z. Components of this is a1y minus a2x. Okay. Now how we go? This is I times this and this goes dou by dou y of a1y minus a2x minus dou by dou z of a2z minus a3y minus j. Delete this column and this row, dou by dou x of minus j. Delete this column and this row, dou by dou x of a1y minus a2x. I am deleting this and this, dou by dou z of minus dou by dou z of a2z minus a3y. Then plus k times dou by dou x of a3x minus a1z minus dou by dou y of a2z minus a3y. Well, when we differentiate this, you see what happens. This is your a1, then this is plus a1, a1 plus a1, then minus j times minus a2 plus k times derivative with respect to x a3, with respect to y this is 0, this is minus a3, this is plus a3. So you can take 2 common, this is a1i plus a2j plus a3k, this is 2 vector a. So we proved the result that curl of a cross r is this. Okay, this proves I have discussed with you some applications on this vector. It is actually a rotational and solenoidal vector. Next we will be meeting very soon, and next this will be subtopic now. It is vector integration, where we have to take line integral, surface integral, volume integral, and terms related to this. Thank you very much. We will meet soon. Thank you. Okay ji.